So the reaction rings press against the thrust-bearing center race to give steering feel and centering action.
Yeah, that part I understand. The worm shaft balancing ring is my problem. You see...
Hiya, fellas. Excuse the interruption, but this sounds like a good time for a general review of power steering operation from the beginning. How about it, Stan?
Okay, Tech. I'll start by identifying the parts. Chet can explain the hydraulics. It's easier to remember the various parts and how they go together if you think of the whole gear as a group of sub-assemblies. For example, we have the gear housing assembly and the powertrain, which includes the reaction and piston assemblies, the steering valve assembly, and the sector shaft. The basic mechanical parts of our power steering gear are arranged about the same as in the manual steering unit. But in the power gear, the recirculating ball parts are built into the worm and piston assembly, and the gear housing acts as the cylinder for the piston. Mechanically, the piston moves up toward the rear for a left turn, or down toward the front for a right turn as you rotate the worm shaft. In other words, it moves the same way the ball nut does in the manual gear. The sector shaft teeth mesh with mating teeth in the power piston so that piston movement causes sector shaft rotation. Viewed from the top, the sector shaft turns counterclockwise as the piston moves upward and clockwise as it moves downward. As the worm shaft begins turning, it threads up or down a slight amount before the piston moves. This slight movement is transmitted to the steering valve by the valve pivot lever and the center race of the thrust bearing. The cylinder head and the housing head hold the reaction spring washers and reaction rings in place against the center race and spacer. The reaction operation is both mechanical and hydraulic, but the hydraulic reaction provides the proportional feel in our power steering, so Chet can tell us how it works.
Okay, Chet, we're ready for the story on power steering hydraulics.
Right, Tech. I'll start with the basic power assist and control functions, and then go on to details of control and reaction operation. We can begin with the gear housing. Two fluid passages extend from the steering valve mounting surface to the interior of the cylinder. The upper port connects to the lower end of the cylinder, and the lower port to the upper end. Now, if you consider the assembly in simplified form, the power piston divides the cylinder into two separate power chambers. Under pressure, the piston moves upward to assist in left turns, downward for right turns. As a result, the effort needed to turn the worm shaft is reduced. A belt-driven oil pump provides the hydraulic pressure and flow which operates the power steering system. Input to the steering valve is at pump pressure. The fluid returns to the pump reservoir through the back pressure valve. Now, to control flow to the power chambers, the steering valve has a sliding spool with lands which open or close the power chamber fluid ports. This spool reacts to the thrust-bearing center race, which moves in proportion to the effort exerted at the steering wheel. In other words, light turning force at the steering wheel produces small movement of the valve spool and steering assistance in proportion. Heavy turning force displaces the spool farther and gives greater steering assist. Now, the steering valve spool centers automatically when there's no turning force at the wheel, as in the straight-ahead position. Under these conditions, the reaction system keeps the center race and valve spool in the centered position. There's no power assist when the valve spool is centered because both power chamber ports are open an equal amount. While the spool remains balanced, fluid circulates through the valve and maintains relatively low pressure in both chambers. In a left turn, the valve spool moves upward. The lower land closes the lower port to inlet flow and opens the same port to return flow. This action blocks off pump pressure to the right turn power chamber as it opens the return passage. At the same time, the upper land opens the upper port to inlet flow and closes it to return flow. This admits pump pressure to the left turn power chamber but blocks the return passage. Now, when system circulation is restricted by a closed valve port, pump pressure increases. And since one power chamber is exposed to pump pressure while the other is blocked off, there is a pressure difference between the two chambers. The pressure difference moves the power piston upward as more fluid enters the lower chamber. As it moves, the piston forces fluid out of the upper chamber into the return line.
And that's where the back pressure control valve gets into the act. Right, Chet?
Right. The control valve maintains some return pressure regardless of steering valve or power piston position. Back pressure on the return side is needed to provide the desirable steering feel, especially in the straight-ahead position. Now, for a turn in the opposite direction, the same hydraulic assist action takes place, but the steering valve and power piston movements are reversed. And, as I mentioned earlier, the power assist continues as long as turning force is applied to the steering wheel. When the turning force on the steering wheel is relieved coming out of a turn, the steering valve spool recenters automatically and power assist movement stops. With the spool centered, pump pressure drops and is again equal in both power chambers. Since the centered valve spool opens both power chamber ports equally, mechanical force can now move the piston back to its balanced position. This allows the effect of steering geometry to return the steering gear to the straight-ahead position without hydraulic resistance on the piston. Incidentally, if the steering wheel is held hard over, the continued turning force on the worm shaft overpowers the centering action of the reaction system. This closes one power chamber port and opens the other, causing the pump to build up maximum pressure.
The pump relief valve hisses when the steering is held hard over. Actually, this condition puts maximum pump pressure against the power piston when it can't move. You could say that the relief valve is telling you to back off a bit so the system won't overheat. Say, Stan, there's another power steering benefit that fits in about here. Do you think you can explain what happens in a power steering gear when the front wheels hit bumps or chuck holes?
Well, I'll give it a try if you'll back me up. When the front wheels hit ruts, bumps, or holes, the wheels try to reverse the normal steering action. In a car with manual steering, this reverse action can cause noticeable wheel fight. However, in a car with power steering, rough road surfaces cause a different reaction. Here, when the deflecting force from the front wheels acts on the sector shaft and power piston, it also moves the steering valve. So, when road irregularities try to reverse normal steering forces, the steering valve spool movement reverses and causes a power assist action which opposes the front wheel deflecting force.
And that opposing action is one of the reasons why power steering makes driving less tiring and safer. Okay, fellas, you've covered the parts and the fundamentals of power assist and control. Now it's time for the fine points of control and reaction operation. Ready, Chet?
Well, the action in either direction tells the basic story, so I'll go to the right. In a right turn, the worm shaft screw tries to thread upward out of the power piston as it produces a downward force on the piston. However, the sector shaft resists the downward force of the power piston because surface friction of the front tires on the pavement opposes steering force. As a result, the worm shaft threads upward a short distance before it moves the piston downward. As the worm shaft threads out of the piston, it moves the center race upward as far as the upper reaction ring allows. This upward movement also loads the upper spring washer. At the same time, the valve spool is moved by the pivot lever, which connects it to the center race. As the center race moves upward, the spool moves downward. Now, when turning force on the steering wheel is relaxed, hydraulic and mechanical reaction forces provide spool centering action. The upward force of the center race against the upper reaction ring is now relieved, so the ring, under power chamber pressure, applies a downward centering force. Along with the reaction ring, the loaded spring washer returns to its neutral condition to help the centering action. When the reaction members reach a balanced position, they keep the center race and valve spool centered until displaced by steering force. In addition to its centering action, the reaction system also balances the hydraulic pressure effect on the worm shaft and provides the appropriate steering feel.
All right, Chet, hold the action right there for now. We're near the end of this side of the record, so if someone will turn it over, we'll continue with reaction system operation. Okay, Chet, tell us about worm shaft balance.
Well, it's like this. The hydraulic surface area on both sides of the piston is equal, so the effect of a given amount of chamber pressure is the same on either side. But in any piston position, pressure in the upper chamber and piston interior pushes upward on the bottom end of the worm shaft. The upward pressure tries to make the shaft thread out of the piston and move the center race away from its centered position. As mentioned earlier, the reaction rings produce a centering force on the center race. However, the hydraulic surface area of both rings is equal, so we need some other means of counteracting the unbalancing force on the worm shaft. To do this, the upper reaction ring groove also has a worm shaft balancing ring, which provides additional reaction surface. In effect, the balancing ring applies the necessary compensating force on the worm shaft. In addition to its balancing function, the reaction system also provides the driver with appropriate steering feel. It does this by resisting center race displacement with enough force to modulate valve spool movement. In other words, center race movement is balanced by hydraulic reaction force. As a result, the valve spool regulates power chamber pressure so that some manual steering effort is required. With this arrangement, the driver exerts about 10% of the total steering force.
Well, that gives us a good go-around on the power steering gear. Now it's time to talk about power steering pumps. It's your turn, Stan.
Okay, Tech, here come the pumps. For the benefit of newcomers, our present power steering systems may have a pump with a .94 or a 1.06 cubic inch displacement, depending on the car model. These pumps are designed to meet the flow and pressure needs of specific applications and are not interchangeable. In fact, both pumps are available in different pressure ratings, so be sure to use the correct unit for replacement. You can easily identify the .94 pump. On this model, the pump shaft end is threaded for a pulley retaining nut. This pump also has a long oval-shaped filler tube. The 1.06 pump has a threaded center hole in the rotor shaft and a round filler tube. The threaded hole is for a special tool required to install the pulley safely. You see, hammering the pulley on causes internal pump damage. Both of these pumps operate on the same basic principle. In the .94 pump, flat vanes are used to produce pumping action. In contrast, the 1.06 pump uses rollers for this purpose. Both types of pump have a flow control valve to regulate fluid flow in the system at all engine speeds. Each also has a pressure relief valve.
Why don't you explain why two valves are needed, Stan?
Okay, Tech. It's like this. Pump output normally increases with engine speed, and without a control valve, pump flow would become excessive at higher speeds. This would waste engine power and could cause the hydraulic fluid to overheat. Now, the flow control valve design differs with pump type. However, since both valves produce the same result, I'll use the 1.06 pump as an example to describe flow valve operation. At low engine speed, spring pressure on the flow valve spool keeps the internal bypass closed. As a result, the entire output flows to the pump outlet from the pressure chamber. As pump flow increases to the first stage of control, the pressure increases and moves the spool inward against the spring. At this stage, the spool starts to uncover the bypass passage and returns part of the flow to the pump inlet. In the second stage of control, at higher speeds, the spool moves farther inward. Here, the spool bypasses most of the pump output so that only the necessary flow is supplied to the steering gear chambers. Now, in addition to flow control, we also have a relief valve to protect the pump and system against excessive pressure buildup. For example, it limits pump output when the steering is held hard over against the stops. As mentioned earlier, this condition causes the pump to build up maximum pressure. The pressure relief valve in the 1.06 pump is built into the flow control valve. Actually, it's a spring-loaded ball valve which causes the flow valve to limit maximum pump pressure. If the flow valve is taken apart for cleaning or other reasons, be sure to reuse the original calibration shims. Each valve has a selective fit and must not be used in any other pump. Now, before I forget, a return line oil cooler is used on some models equipped with axle ratios which result in higher pump operating speed and temperature. In other words, oil cooler application is based on axle ratio rather than the car model or engine.
Thank you, Stan. Now, how's about some troubleshooting pointers?
Okay, Tech. In troubleshooting, the easy or obvious things should come first. For example, if the power assist seems below par, I check the fluid level and drive belt tension before going any farther. If the belt is loose or glazed, it may squeal when the steering is held hard over.
Use a half-inch drive torque wrench to adjust belt tension where the pump mounting bracket has a square hole. And don't guess at the belt tension. Refer to the specifications in your service manual. When you add fluid, be sure to use only Chrysler-approved power steering fluid. Transmission fluid or other substitutes can cause pressure hose deterioration, especially if the system is operated mostly under high temperature conditions. And another thing, if you install a new pressure hose, use the correct part number replacement. These hoses are designed to conduct hydraulic fluid under high pressure and to damp out system noises. In other words, the wrong hose can cause operating noise. And now back to you, Chet.
Okay, Tech. Now, if a pump seems noisy, it's easy to check out. You slowly pour water on the drive belt with the engine running. If this eliminates or changes the sound, the noise is caused by the belt or a pulley. But if the sound doesn't change, loosen the steering pump drive belt and run the engine at the speed where the noise sounds off. If the sound still continues with the pump stopped, you'll have to look somewhere else for the cause, like the water pump or alternator. If fluid level and belt tension check out okay, but there's no steering assist in either direction, the pump flow control valve may be stuck open. This, of course, will bypass the fluid to the pump inlet and lower the pressure. To check for a stuck valve, speed the engine up to about 2,000 RPMs and turn the steering hard over a few times to hit the stops. If this treatment restores steering assist, you'll know the flow valve was stuck and may require service. However, a pressure test is the best way to isolate the cause of steering system trouble. For example, correct pressure at low engine speed tells you there's no obstruction in the hydraulic system, and the pump output flow is probably okay. Then, if the pressure is correct at higher engine speeds, but you get little or no steering assist, it usually means that the pump is okay, and the trouble is probably somewhere in the steering gear mechanism.
Don't try to cut corners by installing a new pump as a cure-all for power steering problems. Just remember that it's hard to explain the charge for a new pump if the trouble's actually in the steering gear. Got any servicing hints for us, Chet?
Well, anyone who works on power steering should be careful to keep foreign material out of the system. Cleanliness is just as important when checking fluid level as it is during a pump or gear overhaul. Now, here are a couple of don'ts. When you adjust the steering valve to correct self-steering or unequal assist, don't forget to retighten the valve body screws before you turn the front wheels against their stops. If you forget, the pressure buildup can blow the O-rings. When you adjust the steering valve, don't hammer on the back pressure valve body, because you may cause the valve piston to jam. It's safe to tap on the end plug to move the steering valve down and on the valve body screws to move it up. Also remember, the lower end of the steering shaft must be centered in the coupling with the gauge hole 13/16 of an inch above the coupling. If the coupling isn't centered, it can load the worm shaft end and cause wander, unequal assist, or returnability problems. Well, that's about it, Tech.
Thank you, Chet, and thank you, Stan. Before I forget, the operating instruction books for our cars now suggest a power-off demonstration of power steering and power brakes. It gives the driver a chance to experience these conditions away from traffic. Speaking of books, I want to remind all bastard technicians that the service manual tells it the way it is. Even if you've heard all this before, dig into those manuals so you'll be up to date on the latest service procedures. And that brings our session on power steering to a close. Be sure to check those reference books for added details which we had to skip in the film. And on any power steering job, always remember to keep it clean. See you all at the next meeting.